Hello folks, my name is Michael Greer, and today I'll be explaining how to implement the ARP networking protocol in an FPGA. So let's go ahead and jump right into it. So ARP, what is it? ARP is the Address Resolution Protocol. Let's talk a little bit about that and understand it before we jump into the FPGA code. So when you have an application on an end computer that wants to communicate with another computer somewhere around the world, it is going to send a series of packets that will scape the World Wide Web. From the application, you'll have a TCP packet, and that will become the payload in the IP packet. And IP is an addressing protocol that the World Wide Web uses. To then take that IP packet and move it along in a local LAN network from your computer probably to the router that then is going to take it further from there, you use the Ethernet protocol. And then the Ethernet protocol, it'll get used as you have routers forwarding it to the next router, in line to the next router, scaping however many routers it needs to traverse until it's able to get to that end computer. So when you have a computer that's connected to a LAN network and it wants to communicate from computer to computer or from computer to the router, it uses the Ethernet protocol. And the Ethernet protocol asks for a MAC address. Now, every internet device that you buy, it is issued a MAC address from the manufacturer. And the manufacturer is allotted a slice of the available MAC addresses from a committee that governs all the manufacturers. A committee governs it because you don't want two internet devices with the same MAC address. So a committee will allot a manufacturer maybe 2 million different addresses, and then it can create its devices and assign them to those addresses. If a manufacturer needs more addresses, they'll talk to the committee, they'll allot them more. So when you connect an internet device to your LAN network issues it an IP address so that it can communicate with the rest of the internet. And these pairings of IP address to MAC address are saved at the router. Now, when you have old connections, the router will time those connections out and delete them from the routing table that has that pairing, because you might have thousands of internet devices connected to that LAN network, and it doesn't have room to store them all. So it's got to just keep stored the actively participating connections. When you want to re-establish a connection, you're going to need to repopulate in the routing table the connection between MAC address and IP address. And the protocol that's followed for re-establishing and finding that data to repopulate the routing table, that is the Address Resolution Protocol. That is what ARP is. So now let's take a peek at what an ARP packet looks like. So this is the ARP packet format. The ARP packet is the payload of an Ethernet packet. And if your router is looking to reestablish that connection in its routing table, it's going to send this ARP packet. It is going to broadcast it to all devices that are on the LAN network. And it does that by setting the destination addresses to all ones or all zeros. I forget what the protocol specifically asks for, but you can find that quickly in a data sheet. So it broadcasts, and at each network device, when it senses the broadcast code, which is either all ones or zeros, it'll bring that packet into its device and it will process it. That internet device will notice that it's an ARP request, and the ARP request, let's look at some of the fields here. We've got the source hardware address, which is the MAC address. That'll be the MAC address of the router that's looking to resolve this issue. Source protocol address is the source IP. It's looking for a target hardware address. That is going to be all zeros because we don't know what that is, and it will state what the target protocol address is. If that internet device's IP address is equal to this target protocol address, then we know that the router is looking for my MAC address. And so what we're going to do is we're going to send an ARP reply packet back to the router. We're going to address its destination to be the router's IP address and the router's MAC address, and we're going to set the source of the reply packet to be what my IP address is and my MAC address. Once the router receives that, the router then knows that it's an ARP reply, so I'm going to be populating my routing table, and I'm going to populate it with this IP address and this MAC address. So that is what we're trying to accomplish. And now we're going to implement that into the FPGA. So let's go right ahead. So let's take a peek at the block diagram. What we'll be implementing today is this ARP response block. This is the block diagram showing the FPGA. Coming into the FPGA, you're going to have a standard reset signal. You're going to have what my MAC address is and what my IP address is, and that will go straight to our response block that we're implementing. This block here, the PHY and MAC, that is a chip that is typically on board the FPGA, and that's just a networking card. What that does is it handles the physical layer of the internet stack. So it'll bring in the packet bit by bit, and it'll assemble it. Once it's fully assembled, it'll let our response block know that we have that packet and it's valid, so this data valid line will become asserted, and then it will send that packet over byte by byte. And it'll give us a clock so that we can clock it in at the speed that it wants us to. So we'll bring the packet in. We'll then analyze the packet. We'll check to see if it is an ARP request. If it is an ARP request, we're going to see if the destination MAC or the destination IP address is equal to our IP address. If that's the case, then we know that we need to send out a reply. So then we create a packet to send out a reply onto the network. We receive a clock line that we're going to use to clock it into the Ethernet card. We're going to present to the Ethernet card that we have data available, and once the Ethernet card acknowledges that it's ready to accept the packet, it's going to send us an acknowledge. And then we are going to send the data byte by byte over at the speed of this clock TX. Once this Ethernet card receives that packet in full, it's then going to send the packet out onto the Ethernet line to get sent to wherever it needs to go. All right, so let's take a peek at a high-level conceptual design. So we're going to bring in the packet byte by byte using a shift register. It'll be 42 bytes long, and it'll shift it in, clocking at clock RX, which is provided to us by the network card. Once we assemble that packet, we're going to check to see if it is an ARP request and if the target IP address is equal to our IP address. If it's not, we're going to go back into an idle state waiting for another packet to come in. If it is, then we know we need to do an ARP reply packet. We're going to create that transmit packet and we're going to place it into a FIFO. Removing from the FIFO, we parallel load into a transmit shift register and we shift out the bytes at the speed of clock TX, which is also provided to us from the network card. The reason I use a FIFO is because the networking card is going to acknowledge when it's ready to receive packets. And if it doesn't acknowledge right as I'm ready to present to it a packet, then it's going to lose that packet. We need to save the packets and send them out when the Ethernet card is ready. And so we're going to just save those values and send them out when we are able. So let's take a peek at some of the hardware that we know that we're going to be using. So on this receive side, we're going to need a match equality check and a request equality check. And we can do that through some bit masking and some bit manipulation. We're going to need that 42 byte shift array here. On the FIFO side, we're going to need a counter that can count the memory locations. So I just chose 8 packets that we can save to send out. We'll need to then instantiate the FIFO memory itself. On the receive side, we're going to need a counter that counts 41. It'll count the amount of bytes that it's going to transmit out, and we'll need that 42 byte shift array. These two positive edge detectors come from the fact that we are given these clocks. This clock here that is going to govern the FIFO, we're going to create that, and it has to at least be faster than these two so that it can sense the place and remove control signals that are going to be inside of these state machines. And if this clock is 2, 3, 4, 5 times faster than either of these clocks that are presented to us, this clock is going to sense that place or remove signal from the state machines. It's going to clock it in multiple times. And we're either going to have multiple removes happening or multiple places, and we want to avoid that. So we use a positive or negative edge detector just to detect that edge only once, and then it won't go off for future clock-ins. So let's take a peek at the state machine. So the state machine, from the receive side, we're going to start in the idle state. Once we see that data is valid, then we're going to shift. This is a control signal that's going to shift into the receive byte shift array. We're going to continue to shift in until the data valid line becomes deasserted. At that point, we do a check if it's a match or request, and if it is, then we assert a place control signal for the FIFO to sense. On the transmit side, we're going to check to see if there's data in the FIFO, and that will come from the counter that counts up to 8. Once we notice that there's data in the FIFO, we're going to do a parallel load. This is a load control signal that will be a part of the transmit byte shift array. And then we have a remove control signal that's going to remove from the FIFO. So at that point, we're going to wait for that acknowledge to come from the control signal. And we're going to be presenting that we have data available to that device. Once we sense the acknowledge, we're then going to start shifting out. We're going to shift out the first byte, we're going to reset the 41 counter, and we're going to still assert that data is valid. The reason we're counting up to 41 is because it's 42 bits wide. We shift out the first bit here, and we'll then shift out the remaining 41 bits here. We increment the counter, we shift the bytes out, and we still assert that data is valid. Once we've counted up to 41, we know that we've shifted out all 42 bytes, and we'll go back into the idle state, and then we can send out more data if it's in the FIFO. All right, so next, I just take the state machines, and I have a clear view of their inputs and outputs. I then am able to organize, based on those inputs and outputs, what devices I need that I'll then need to code. So we'll need some equality checks, we'll need the byte shift arrays, the FIFO memory, the positive edge detectors, and the counters. So let's go ahead and take a peek at my code. So this is my code. We have my ARP module here, standard inputs and outputs. We have the shift arrays instantiated here, FIFO memory instantiated there. These are registers that will hold the counter values, and these are the outputs to the state machine. The assorted hardware, we've got the positive edge detector and the negative edge detector. We've got instantiated here the two counters. This is the matching hardware. We've got the 2 byte shift arrays. And then we've got the FIFO. And then below that, state machines for the transmit and a state machine, state machine for the receive, state machine for the transmit here. Next, we're going to take a peek at the test bench. The test bench is going to have a state machine for itself, which is going to transmit a byte to the module and receive a byte from the module. I have functions in here that send and check an ARP request. I then here have a release packet. The master loop for beginning it all is going to be right here, and then I call my functions that will test. I then just have standard displays that are going to display packets that are received and packets that are sent.